All right, cool. Thanks, Abe. So as our last interactive part of the tutorial, we're going to use some of FireSim's debugging features. And then I'll talk a little bit about some profiling features and instrumentation too. So a quick review of the sort of roadmap we followed so far in the tutorial. We made it all the way down here to FireSim FPGA Accelerated Simulation. And in this section, we're going to ask the question, well, everything is great when the simulations just work like they did in the previous section. But what happens when you're developing some new piece of RTL? And then inevitably, there are bugs in the design, right? So we're going to try to understand what's going wrong in a potential design using some tools now. So quick agenda. So we're going to talk about how to debug problems that appear deep into a long-running FPGA simulation, right? So these are problems that appear so far into simulation that it's impractical to run them, for example, in software simulation. Of course, software simulation is useful sometimes, so we'll talk about how to simulate an entire FireSim simulator in software at the end, and talk about some of the advantages of doing that for maybe your own work. Oops. All right, so what is the use case here, right? It's for when software RTL simulation isn't doing well enough, right? So, or going far enough in the simulation, right? So everything looks okay in software simulation because we just can't run that many cycles, right? So there's still a bug somewhere, right? And the bug only appears after several hours of running Linux on the simulated hardware on an FPGA. So then we need some way to introspect on what's happening on the FPGA. And classically, with just running FPGA prototypes, this is a pretty bad situation, right? The only real tool you'll get to debug that situation is an ILA. And FireSim will support that too, but we'll have a bunch of other nice features also that will let us debug systems as we get deeper and deeper into simulation time. Some of these that we'll cover today are a tool called TracerV that basically lets you grab like 100% fidelity instruction traces off of a RISC-V SoC that's simulated in FireSim. We'll talk about AutoCounter, which is a way to automatically inject performance counters that are, again, sampled out of band without perturbing the system you're modeling. And then some debugging features, namely synthesizable assertions. So assertions you write in your RTL code will actually fire on the FPGA instead of just disappearing when you go through the FPGA flow, as well as prints. Same deal. You have prints that will show up, for example, in software RTL simulation in your RTL. We can make those same prints be pulled off the FPGA and logged to disk. OK, so let's first, though, talk about ILAs. So ILAs is a standard tool you would probably expect to use with an FPGA, right? Most FPGA vendors provide this as a standard feature. It's some hard IP that sits in the FPGA that can be wired up to whatever logic you've put on the FPGA and can basically capture some recording for some amount of sampling window time, right? And you define some trigger that is going to cause the sampling to occur, and then it starts logging information. You can pull that off on software. So in FireSim, we support this with annotations in our design. So basically, what we can do is automatically insert ILAs with an easy marker in your RTL design. And then all of the wiring that has to happen to pull that off of the FPGA is handled automatically by FireSim. And in particular, on AWS F1, we'll also automatically launch debug bridge and server to bridge that ILA information between the FPGA hosts. So you saw just now that the run farm machines are separate from your manager instance to bridge that information between the run farm host and the manager that you're actually accessing. So as I said, we're going to automatically annotate, or we're going to annotate signals that we're interested in the chisel source code itself. And we'll automatically generate all of the ILA IP for whatever vendor you're running on that is supported in FireSim. And then we'll automatically expand this out, wire it up to your actual signals, even if they're deep inside a module hierarchy, and pull them out to the top. And then we have this remote waveform capture and trigger configuration mechanism too. So as a quick example, you don't have to do this, but for example, if we had a bug in Boom, let's say our non-blocking data cache is causing a hang after Linux boots, we can mark some signals with this FPGA debug flag, and then they get wired up to an ILA for capture later. So what are the pros and cons of using this technique? Of course, here we're using the vendor ILA. So there's really no notion to that ILA of what's in the simulated world, what's a maybe model wrapping the simulated world, what's just infrastructure connecting the FireSim top to the rest of the FPGA. So there's not really anything emulated from the perspective of the ILA. You're seeing exactly the signals that are changing on the FPGA. So this has a positive in that if we need to debug FireSim itself, we can attach wherever we want and capture signals from the simulator world, including the bridges and the various models and so on. And again, you're running at FPGA simulation speed, just like many of the other tools we'll talk about here. So of course, we can debug at sort of megahertz instead of kilohertz. And we get this ability to change triggers that cause capture to happen in real time, of course, depending on what the vendor's platform supports. There are a few cons, though. So if we want to change what we're actually capturing, we usually need to run an entire bitstream build. And usually we have a limited sampling window size, think like 1K, 4K, something like that. And it consumes FPGA resources, but of course, it's usually not that bad. Yeah.
Difficult to align the different timescales. Because if my simulated machine has something happening at clock cycle 1000, it's most likely not the clock cycle 1000 I'm seeing with ILA.
Yeah. You're exactly right. So this is a tool we'll primarily use for debugging the simulator, and we will generally not point people to this for debugging their target design modeled in FireSim. So there are better ways to do that we'll get to. Yeah. So this is usually, if you're debugging on the FPGA, this is just like for like an FPGA prototype, this is kind of like the last resort tool you'll use. Yeah. Okay, okay, this clicker is dying. Okay, so the next tool I'll talk about is TracerV. So like I mentioned earlier, TracerV is basically going to give us a full instruction trace captured from all of the cores inside of our SoC, captured completely out of band. So what I mean by that is, unlike that perf example that I talked about earlier today, where say, we want to capture a flame graph or find hotspots in software using perf on a real system. If we do that and we try to capture very high fidelity data, eventually just perf ends up running most of the time and we're perturbing our system and not getting realistic results. With TracerV, because we are able to stop the world, including the hardware, we can capture fully out of band instruction traces. So every time we have a cycle of instruction trace data, we fill some buffer on the FPGA, and periodically that buffer on the FPGA gets drained. But if that buffer gets full on the FPGA, we can just stop the simulation from advancing, and it doesn't affect what's happening inside the design. So it remains deterministic, even though we've added this debugging infrastructure to it. There's a bunch of stuff that's wired out by default in Rocket and Boom-based design. So you can get like the instruction address, instruction contents themselves, privilege level, and all sorts of other stuff. And using this, you can actually pretty rapidly generate several terabytes of data that you need to process in some way. Luckily, you may be running this on the cloud if you're using F1, so you can process this data pretty easily. And so the nice thing here, and this is sort of a very one-slide summary of an ASPLOS paper we had a few years ago, but basically this lets us very easily profile very complicated stacks. So in that paper, back I think ASPLOS 2020, we were essentially asking the question, okay, we have FireSim now, and we'd like to keep doing this data center modeling work. But of course, real data centers have Xeons with big beefy network cards. And if you look at the original FireSim paper, it says, okay, we built a 200 gig Ethernet NIC, but when we boot Linux on our kind of wimpy Rocket-based system and try to run network benchmark over TCP/IP on top of Linux, we only get a gigabit per second, right? A 200x reduction. So we're trying to understand what was happening in this huge stack, right? It's the benchmark application. It could be the Linux port, which a few years ago for RISC-V was fairly immature. It could be our own driver that we wrote for our own NIC RTL that we wrote. And it could just be a bug in the SoC generator itself. So really the problem here is that we wanted complete fidelity because we didn't know where the problem was in the first place. And so what this lets us do is capture flame graphs, and I'll show you some examples in a few follow-up slides that kind of show you hotspots in the code, but across all of the code running on the system. So that includes the operating system, it includes the network driver, it includes all the interrupt handlers, things that you traditionally can't really get to with perf. And in that ASPLOS paper, we basically took this and we were able to optimize that Rocket chip-based system so that it could actually compete with a Xeon in terms of network performance because we had these sorts of tools that let us do it fast. Yeah.
Questions. First one, how does TracerV deal with virtual versus physical analysis?
Yeah.
They will be different at all of these levels.
Yeah, so it has context. So FireMarshal has some add-ons that let you generate a bunch of extra collateral that tell you, here's all the debug information for the kernel, for various user space applications, for the bootloader, all of that stuff. So it kind of knows, where it is in the stack and what to correlate it against.
Second question, being able to export hardware state as high throughput, can that also be leveraged for non-RISC-V instructions? Meaning, can I leverage the same infrastructure to export state from a non-software program accelerator?
Yeah. So you can wire up. Okay, so this infrastructure is, you can think of it as sort of a special case of the printf synthesis that we'll get to, which will basically answer your question, I think. So you can print random information coming out of, say, your accelerator or whatever, and log it to disk the same way. This is basically just a special case of that can do extra processing because we know what the contents of the trace are. Yeah. So TracerV is a FireSim bridge. So it kind of fits into the, I don't think we cover bridge design here. There's some information about it in the docs, but FireSim bridges are basically like something that usually takes data from like the top level of a simulation running on the FPGA and bridges it out to somewhere else, either the host or some FPGA attached resource and so on. So yeah. Right. Yeah. So here we're using kind of the standard RISC-V trace interface that's exposed at the top of Rocket Chip and Boom and so on. Yeah. Cool. Any other questions? All right. So one issue here, if you just start tracing everything, is that your trace files can be huge. So generally, we're really only interested in a specific part of the program, right? Even in our previous case where we wanted to capture full stack information, we didn't want to capture, Linux boot in our flame graph. So we only wanted to start capturing when we knew our benchmark was running. Even though we are able to capture the whole operating system, everything happening underneath, we wanted to only make sure it's running for the benchmark. So TracerV has a bunch of different trigger functions. You can trigger on a specific program counter, on a unique instruction, or even just an absolute cycle count. So one neat trick you can play in the unique instruction case is if you say have a C program at the top that's running your benchmark, you can kind of write in an assembly fragment that does add I into register 0 with some immediate that to keep track of, so that you know when to start and stop TracerV. So these are sorts of triggers you can do to cut down the amount of data that gets generated, and to know that the data you're generating is actually the area you're interested in. Okay, I basically already talked about this. We're running out of time, so I'll skip the flame graphs thing. So some pros and cons here. So a nice thing about TracerV is that it's completely out of band. So there's no impact on software execution or the hardware behavior of your system. And it's a more software-centric method of debugging. So of course, this is assuming you have an SoC that has processors, and you need to debug software usually running on those processors. And it'll generate a large amount of data. You'll notice that that's a pro and a con, depending on what you're trying to do. One con here is that it will lower your simulation performance. So for kind of a vanilla rocket chip-based design that you could push through at like 150 megahertz, when you start adding this logging functionality, it's going to cut it down to something like 40 megahertz. And that's, of course, just because we have to keep up with logging all the information ultimately to disk. There is little hardware visibility here, right? So you're getting an instruction trace, but you may not necessarily know what is causing that output to be produced. And we'll get to some tools that let you help with that later on. Okay, before I move on, any other questions about TracerV? Okay. So next feature is called AutoCounter. So AutoCounter is kind of the hardware corollary of TracerV from that previous ASPLOS work. So of course, we wanted to construct flame graphs to understand what was happening in software, but there was also a hardware component to our performance degradation, right? So what we wanted to understand in this example you see on the right-hand side of our NIC RTL design is, are, for example, all of these queues properly provisioned in terms of size and depth in our NIC. And so we can stick in performance counters, of course, by hand and wire them all out to the top and try to pull them off. But that's kind of a pain. So we added this functionality where we can basically automatically inject performance counters into our design and have them, for example, track state change of certain signals and count those, for example. And again, you annotate these in your RTL. They get automatically pulled off of the FPGA and logged to disk so you can understand, for example, maybe what the maximum occupancy of, for example, the send queue is. Here's just an example of using AutoCounter. We're not going to do any of this interactively, so I'll leave this later for you to look at in the slides. So just as a quick example, what happens when you run AutoCounter? You get a CSV like this. A lot of this is not super important to understand right now. But basically, what's going to happen is you're going to get one of these CSVs per clock domain in your simulation. And as you move to the right, you'll have more and more columns for the various counters that you have in your system. And as you go down in this file, you'll get more and more samples. And the number of samples, of course, depends on the sampling rate you set and so on. And you can set the sampling rate to be really high, and that'll just slow down your simulation, but not affect the actual outcome of your simulation. So a couple pros and cons here. So this gives you sort of a nice macro view of execution behavior. So rather than looking at sort of waveforms directly and trying to understand performance there, you get some designer insight into what is happening in the design to kind of abstract away information in a more sort of easy to understand form for performance debugging. This handles the same trigger functionality that we talked about earlier, so you can control when these things are captured and not. And another nice thing here is a lot of designs will have pre-configured cover points. So cover is one of the APIs we use to capture performance counter information. And so if the RTL designer already put in these cover points for other purposes, they're essentially marking interesting places in the design for you already, and we can capture those automatically. And we can control the granularity of capture at the software level. So again, you can runtime control the trade-off between fidelity and simulation performance. Cons here, again, adding new counters means you have to regenerate FPGA images, and you'll have some performance degradation depending on how many counters you have and how often you sample them. Okay, last thing I think we'll talk about today is synthesizable assertions. Oh, no, second to last thing, I lied. This is synthesizable assertions. So assertions are a great way to kind of encode information about what the designer. Quick question? Yeah. Yeah. Are what? So they're in band from a simulation performance perspective, but not from the perspective of the design. So like if you have, for example, if you have performance counters baked into a real processor and you try to sample them very often, right? You can affect the state of software or the performance of software that's also running on that processor. Here, the sampling is happening completely out of band. So instead of trading off like accuracy of the sampling versus how often you're sampling, we're trading off simulation performance versus how often you're sampling. Yeah. So it doesn't affect the thing you're trying to measure. Yeah. Any other questions about performance counters? Oh, yeah.
I guess view of how like much of a performance impact it was going from 150 megahertz to 40.
Yeah.
Was that trying to sample it every single cycle?
Yeah.
Okay.
Okay, cool. Okay, yeah, so back to synthesizable assertions. So the idea here is that as the designer, you're capturing some information about the behavior of certain signals in these assertions in your RTL, right? This is just generally good practice when you're writing RTL. Normally, when you take RTL like this and push it onto an FPGA, those assertions just get discarded. So in FireSim, what we can do is automatically transform those into hardware modules that can detect an assertion firing and pipe that information off of the FPGA. So as an example from Boom, there are some asserts that tell you if the ROB is behaving unexpectedly. In this example, overriding of an entry that's already valid. And if you run this, not actively right now, but for example, if you run this and an assertion fires, you'll see information like this show up in the Linux boot log, for example. So this was a real bug that existed previously in Boob. It would have taken 62 hours to hit this assertion in software RTL simulation, but we can get here in a few minutes in FireSim. And you'll notice that this assertion has a bunch of useful information, right? It tells you exactly which assert fired, what that line of code is, and of course, where that line of code is in your source, right? And then the simulation will fail and die, and you can introspect further. Okay, so any questions on assertions? Yeah. 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 Right. Yeah. So they still have to synthesize onto the FPGA, right? Like, yeah. But besides that, yeah. Like it won't show up in other flows, like ECAD flows or Hammer or whatever. Yep. Yeah. Yeah. So people have this isn't quite what you're asking, I think, but people have thought about adding functionality in Chisel for more complicated sorts of assertions, like assertions that take place over multiple cycles and stuff like that. I don't think any of that stuff got upstreamed anywhere. Yeah, so that's kind of the closest thing we've thought about. Yeah, but not like using other languages or any sort of thing. Okay, okay, I think this is the last one. So the last thing I'll talk about is synthesizable printfs. So again, the idea here is that we want to enable closer to software style debugging, right? So a common way to debug RTL and software simulation is to throw prints in there, especially around things that you would call like a transaction, like a ready valid handshake, stuff like that, or maybe accessing the memory system. And so we would like those prints to also be visible when we're running on the FPGA. And of course, we can do the same kind of thing we did in the previous example, is tack on some extra hardware that looks at certain printfs that you've marked as something that's interesting that you want to pull off, and pull that off of the FPGA. So here's another example. If you want to understand the memory system behavior of Boom, there's a printf here that's printing a trace of all loads and stores in Boom, and we can wrap it in the synthesize printf call. And when you run this through FireSim, it will essentially get pulled off and logged into a file on the host system, and you can access, as the simulation is running, a live trace of all the loads and stores that are coming out of the system. Okay, any questions about printf? I know we're going super fast now because we're running out of time, but all of this is documented on the website too. Okay, so wrap up here. Again, a nice thing about printfs, because baked into FireSim, we're running at FPGA speeds. We have the same trigger functionality as many of the prior tools I've talked about. And generally, this will consume less FPGA resources compared to something like an ILA, because we don't have to buffer it as much on the FPGA, although that depends exactly on what you decide to capture. And key signals can also have pre-written assertions in the case of assertions in reusable parts that you might be using. Some cons for printf synthesis and assertions. Again, this isn't quite as good as waveforms, although depending on who you ask and depending on the sort of RTL you're writing, you might be able to get away with just having printfs on sort of transactional interfaces to understand what's happening in the system. Another con with assertions is that they're best added usually when you're writing source RTL and you kind of have the concept in your head rather than trying to debug after the fact. And then a final con here is if you add tons of printfs, of course, the simulation is going to get really slow. There's just too much data to pull off of the FPGA every cycle. So one more feature I will quickly highlight is Dromajo Co-Simulation. So another way to find bugs in a design is to have sort of a golden model of the design and compare the execution of that golden model, usually written in a simpler style, like just a software program, and compare that against the RTL running on the FPGA. So one tool we can use to do this, comparing Boom's execution against a software model, is with a tool called Dromajo, and that's also something that's supported in FireSim. Okay, So let's see. Okay, maybe we should skip this. I think, all right, here's what we can do. So these slides are already on the website. We'll leave the instances running for, let's say, until like the end of today. So we're going to skip this for now in the interest of time, but you can come back here and run this yourself later. This is an example of running a design with printf synthesis for real, just like we did booting Linux an hour or so ago. And you can capture the printf and see the output and see it live. Okay, so I will quickly talk about software RTL simulation as a tool for debugging FireSim simulation. So we can kind of start at the top of this flow chart, say, okay, my FireSim simulation is not working, or my RTL is not working inside FireSim simulation. So we can ask another question, which is, what am I actually trying to do, right? If we are just modifying internal simulated target hardware, not adding endpoints, we might want to do just target level software simulation like we did this morning, right? On the other hand, if we're making a bunch of changes to the simulator itself, there are different ways to simulate the whole simulator called meta simulation and FPGA level simulation that we'll talk about now. All right, so what are the differences between all of these things? So target level simulation is a software simulation of your target design, right? That's exactly what we did this morning, running a Chipyard design through Xcelium and getting a trace coming out of that thing. You can also generate waveforms this way, and you don't have any of these host FPGA resources, right? Of course, one problem with target level simulation is that you're using sort of whatever IO models the target level simulation constructor tacked onto that thing, right? So in the case of Chipyard, that can be something like DRAM sim attached to your memory interface. Meta simulation, on the other hand, is a software simulation of an entire FireSim simulator. So what that means basically is we take our design, right? We apply transforms to it to get a FireSim decoupled simulator. We tack on all of the models that we would normally tack on around it. So like the memory model, maybe an Ethernet model, and so on. And then we take that whole thing and simulate that in software, right? A nice thing here is that we get identical performance, whether we're running in this software simulator from a measured performance perspective of the target. We get identical performance between the software simulator and stuff running on the FPGA. So if you run software on this and try to measure the performance of your target system, I don't mean simulation performance. If you try to measure performance of the target system, you'll get the same exact results from running in meta simulation as you would running an actual FPGA simulation with FireSim, right, on an FPGA. And of course, the only difference there is that the software simulation of the FireSim simulation is going to be much slower than the actual FPGA accelerated version. There's a third column here that probably you will never have to use, which is FPGA level simulation. This is a very confusing term. This is a software simulator using a lot of Xilinx IP models to basically model the entire shim around the FPGA. And this is really for debugging interface problems between the FireSim simulator and all of the Xilinx IP that wraps it that eventually goes onto the FPGA. So I would basically just ignore this last column. It's not very important. Okay, I just said all of this basically, so we're going to skip it. And I'll talk about some performance stuff real quick. So these are the top 4 rows here are basically the 2 sorts of simulation you'll probably be most interested in. One is just target level simulation. That's what we did this morning. And the next set of 2 rows is meta simulation, which basically adds all the FireSim wrappers and lets you measure performance of a FireSim simulation of your design, right? And you can see that overall simulation rate here is pretty comparable. Okay, we're going to skip this. This is what you would have seen. Okay, so lastly, we do need to do this. So you should go ahead and run FireSim terminate run farm here. This will kill your FPGA instances so that we stop getting charged money for them. So run this real quick. This is the most important command in the whole tutorial. All right, how are we doing? Good. All right. So as long as everyone got the command, I'll wrap up here. So again, our vision here, as we sort of talked about at the very intro of the FireSim session, is that we want to build simulators that are not only fast, not only debuggable, but really have introspection capabilities as close as we can get to software simulators. And we're still working on a lot of these things to get closer and closer to that sort of stuff, right? But I just wanted to show you here that we have some of these tools that let you get much better introspection capabilities into what's happening on an FPGA in a FireSim simulation than if you were to just run something like an FPGA prototype. So just a final slide here that has pointers to documentation for all of the things that we talked about here. There is much more content, much more description on these documentation pages than we can cover in these slides. So with that, I'll take any questions as we wrap up and move back to Abe.